down from the top, and we make maybe 10 passes, 11 passes. Everything is fine. The surface is beautiful. Looks like a mirror. I think this is going to be no problem at all. We make pass number 12, and the vibration is so horrible. The tool cuts through the wall. A little piece of the wall wound up around the tool like opening up a sardine can, and just ruined everything that was done before. So now, how is that possible? What's the mechanism that would make that happen? It seemed maybe it's a forced vibration problem. Maybe it's chatter. There was a big debate in the laboratory about it. We couldn't figure it out. So we decided maybe the swastika part was not the right thing. Maybe we need a real part. Let's try to make something that looks like something they're making out of sheet metal now. And this is the one that Boeing gave us. And so the whole part was about this size, right, like that, like that. And it had these thin sections, these little ears that stood up in the air. I don't even really know what this part is. I don't know what, but I presumed that there was some kind of a hole that was going to go through here, and I don't know. Anyway, so it looked more like a real part, so we tried to cut that one. Now, I do have a photograph of that one when we cut it, and you can see that this one is also pretty bad. There's a lot of chatter marks over here, there's chatter marks over there. Cut through the top of that ear by accident. I mean, it was pretty bad. And again, the same kind of thing. The first few passes were okay, surfaces all look good, and then it turns bad. And so we're trying to figure out what the cause of this is. Here's a close-up on one of those ears. You can see the chatter marks. So we started making recordings of the sound. We're listening to the teeth hit the workpiece. And this is a recording. This is actually the one that, at least for me, unlocked it. I think that everybody who was in the room at the time thinks that they figured it out. And there were quite a few people in the room. I don't want to pretend like it was just me. I mean, Tom Delio was involved, of course, and Bob Winfo was involved, and Britt Cobb was there, and Chuck Bales, and I think every one of us thinks that we did it. But the thing that unlocked it for me was this. There was this one pass, and we're recording the sound, and that's the sound. And early in the cut, the sound that we hear is the teeth hitting the workpiece. And this is frequency across here, and I'm going to show you a few graphs and only one equation, so don't get too worried. This little dot up on the top of that means that that's the sound of the teeth hitting the workpiece. But a little later in the cut, the sound changed. The frequency shifted, and the little dot is down here now, and the frequency changed. So now what can account for the change? Right? That's not. The wall didn't change that much. These things are only a fraction of a second apart, but something happened. And what happened is, after you see it, it's kind of obvious what happened. The teeth are hitting the bottom of the wall down here, and the frequency got just right that the teeth hitting the bottom got the wall excited, so the wall started to vibrate, and the wall vibrated enough that it started to come into contact with the teeth farther up on the tool. So now the depth of cut went up. And when the depth of cut went up, that made it unstable. So it's chattering. The second sound was the chatter sound. So this was like a trigger. Once it made contact, then boom, it was unstable. It ruined everything. After you see it, the solution starts to be kind of obvious. It's like, aha, if we're only cutting it down here, why do I have teeth up there? Right? I don't mean to cut that. So let's get rid of those teeth. So these are solid carbide tools at the time. You're going to remove the teeth. You got to do it with the diamond wheel. We didn't have a diamond wheel, so we ordered a diamond grinding wheel. And I'm sitting for 4 or 5 days waiting for the wheel to come in. I think we got it. I can't tell for sure. Wheel comes in. We manually ground those teeth off, and we cut the ear again, and it's beautiful, smooth all the way down. Well, it's got a little bit of a mark on it, a little bit of a witness mark, because the back corner of that tool is still a little sharp, and it made a little scratch on the surface. And so we went back and we nicked off that back corner, and we ran the part again, and here's the same ear. So I say we cracked it, right? Then I know what to do. I got the strategy for cut what's stiff, leave the thin part behind. Got to use a tool that has a relieved shank on it so it doesn't touch the surface that I already made. And how thin of a part I can make means how far down am I going to remove the teeth on the tool. If I want to make a really, really, really thin part, then I have to remove a lot of the tooth. on the tool and leave it like almost like a disc on the end of a rod, you know? And so, in fact, we made some really exquisitely thin parts like that, and these are commercially available tools now. Lots of companies make them. You might be interested to know that when we first told McDonnell Douglas about the solution, they didn't like it. Can you imagine why? No, not because it took it longer, but that's a good guess. It actually was faster. The cost was less because the cost was not in the aluminum. The cost was in all the hand labor to do the assembly and all the special tools that they had. And they can't even keep track of the tools, and you have to manually put the holes in for the rivets, and the cost savings was huge. The reason they didn't like it was because they had a process in place that when these tools wore out, they cut the end of it off and reground the end of it, and they had a new tool that was a little shorter. And now I'm telling them when the tool wears out, the cutting part is gone, you got to throw it away and get you a new one. And that didn't look very good.